So let's start this week by talking about wind. We spend a lot of time talking about pressure, temperature, humidity, moisture. Wow, all that's really fun, but how the heck does the moisture move from one location to another? Why does pressure change? Where does the air flow? In other words, why am I getting high pressure, low pressure, and the impacts they bring to the weather? Why is there a front that develops between them? All of that kind of comes out by the wind. So I have a big high pressure sitting right over West Virginia right now, 1037 millibars. You'll notice the wind on the east side of the high is blowing out of the north, south side is blowing out of the east, west side is blowing out of the south. Interesting, isn't it? It's clockwise, just like we've been talking about. My question to you is, why is it clockwise? Why does the wind flow that way? When you drive a car, why does your car go in the direction you want it to go? Why does it pick up speed? Why does it go through the curves okay? There's something that controls all of that, and something that controls the wind as well. So let's look at that. We're going to start from the beginning on this slideshow here a little bit and see what we can learn, right? All right, wind and weather. My question to you is, like I say, I want to know why the wind blows. What controls things? So let's go back here a minute. All right, so we're going to talk about let me restart this slideshow then, since it's not going to behave. We'll close out this and we'll start a slideshow. So, wind and weather. So what are the forces? Here we go. Here's the key word. What makes the wind blow? What makes the air move? So, wind is just the local motion of air. So, force. It's something that alters the motion of an object. If your car is at rest and begins to move, some force had to be applied. That force probably was your motor kicking up. If you go running, you're actually applying a force to your body to make it move down that trail. So their force, and the power of a force is equal to the mass times the acceleration. So as you gain speed, there's how much you weigh. The molecules you have in an object, the more the mass is. And there are a lot of forces that act on the wind. We have air pressure, centripetal force, Coriolis effect, friction, gravity. So let's start simply with air pressure. Air pressure is the high pressure in one direction, low pressure in another. And the atmosphere wants to make everything equal. So think of high pressure as being like a mountain and low pressure being like a valley. And what happens? If you started a rock tumbling down the mountainside, it's going to go down into the valley and settle there. Well, the same happens with wind, with air pressure. air pressure is exerting a force from its high mountain, high pressure, down into the lower areas. So that is the force it's exerting. The greater that force is, the tighter the pressure gradient. So in other words, if I have a bunch of isobars all tightly packed, that's a very tight pressure gradient. If I have one go 1,000 miles, it's not a very big pressure gradient. So the pressure gradient force is based on how closely together these isobars are. Another force, your car moves around a corner. Well, if the engine just continued to move, it would go straight. Turned that steering wheel, you applied a new force. You changed it. That force is centripetal force. When you see they're going around in a circle, it's an extra force. So now we have two forces. We have regular straight line force and we have centripetal force. And that is so. What is another force? All right, this is a little more confusing. The application of the Earth. So think about it. If you were sitting at the North Pole, 24-hour day occurs. Did you move at all relative to the outer space? Not a bit. However, if you're set at the equator, you move 24,000 miles, the distance around the equator. So that generates a force in the atmosphere. So the fact that the closer you get to the equator, the more you're moving compared to up at the poles where you're not moving at all. So in the northern hemisphere, this creates a deflection to the right. In the southern hemisphere, it's to the left. So if I have a pressure gradient force that goes from 30 degrees north to 60 degrees north, and the low pressure is at 60, high pressure is at 30, the wind that would be heading straight to the North Pole instead is going to turn to the right. And the closer it gets to the North Pole, the more that turn is going to be. There'll be less deflection down towards the equator, where there is actually none. Kind of counterintuitive. Where it's moving the fastest, you're not getting any deflection. Where you're moving the slowest, you're getting the most. Friction is another force. The reason that we use rotating tires, rubber, circular tires, it reduces friction. If you had square tires, besides the bumpies, you would have increased friction. So the fact that the earth generates friction against the air. Think about it. If you have a mountain's making the air go up and down over it. That's a lot of friction. However, if I have a flat water surface, there's not much friction. Now, in fluids, part of that friction is generated by turbulence as well, reflected in that. So there's more friction down towards the ground. The higher up you get, there's less, but there is turbulence. When you're flying an airplane or in an airplane, you bounce around sometimes up in the atmosphere. That's probably from turbulence. There's another force, gravity. And so you understand this, gravity is made up of two parts on a rotating Earth like we are. Gravity is the attraction between objects. So all that is saying is the atmosphere, the air is attracted to the Earth. They're pulled together. However, the Earth is spinning, so there's a centripetal force that's projected out, away from the Earth, wanting you to go outwards. So gravity on the Earth is the pull between the two objects and the centripetal force. So there's two components to gravity on a rotating Earth. And because of that, while the centripetal force is very small, it works out to you get an acceleration or force of about 9.8 meters per second. So if I dropped an object in a vacuum, it would pick up speed at the rate of 9.8 meters per second. So you could calculate literally how fast that object would be going in, say, 10 seconds. So now we've seen all the different forces. We know there's a rotation, and there actually is a heck of an air pressure gradient out there between the surface of the Earth. We've learned that pressure drops in the vertical. There's less and less pressure the higher up you are. Well, you've created a pressure gradient that direction. So why isn't all the air just leaving the Earth? Gravity. Gravity holds those air parcels in place. It's created a static equilibrium. It's called hydrostatic equilibrium, actually. And the impact of gravity pulls down the air parcels. The vertical pressure gradient wants them to rise. Because they're equal in hydrostatic equilibrium, yes, a parcel can rise or a parcel can sink, but it's going to do it at a constant velocity. That is why we are able to have an atmosphere. Now, we're going to talk about some other types of air motion. So if I told you, if you looked at high pressure and the air is going to begin to turn to the right, you still have a pressure gradient force, pushing it from high to low. Eventually, they become equal. And when they're equal, the air is going to move along a straight line. That's a geostrophic wind. We're not having any other impact than Coriolis pressure gradient. That's it. So understand that. The geostrophic wind. This occurs usually in the upper atmosphere, above the surface area. Another interesting thing, you can have circular winds. I showed you the winds coming around high pressure on a weather map. Well, in this case, you have centripetal force. It's always changing toward the high pressure because the winds are circulating it. So you have the pressure gradient force out from the high. You have the Coriolis force, which defects to the right. Assuming they came equal, they would be geostrophic wind and they'd be balanced. But when we add the gradient wind, we add the centripetal force. All that does is change the motion to a circular motion. Low pressure, same thing. All right, as we get down towards Earth, we add friction. There's more and more friction the closer you get to the ground. At the ground, there's a lot of friction. So what does that do? Well, it's going to slow down the wind. If I slow down the wind because of that, Coriolis impact is not going to be as great because the Coriolis effect is based on the speed of the wind. So because of that, wind will begin to blow towards low pressure and away from high pressure. That is why when you look at a surface weather map, you'll see winds that are clockwise around the high, but they're always tending to blow outward slightly. Around the low, they'll always tend to blow inward. And here you can see that. Now, the atmosphere, what you do in one part of it, it's a fluid. So you're moving it. If I have divergence at the ground level, then the air above it's going to want to sink down, take its place. So you probably have convergence aloft. By the same token, if I have divergence in the upper atmosphere, I probably have convergence at the ground and rising air. Oh yeah, we learned that rising air causes temperatures to cool faster and we get more precipitation that way. So understanding this concept that horizontal convergence at the ground pushes air up, divergence aloft pushes it apart. Convergence aloft pushes air down. Divergence at the ground pushes air apart at the ground and causes sinking air. Which ones are going to give you good weather? I want convergence aloft and divergence at the ground if I want sunshine. If I want clouds and I need some rain, I just want the opposite. So there you go. Now you've learned all you want to know, right? Probably not. But that's all we're going to talk about with how winds work.